Hi, welcome to my video presentation on my research project titled Noise-Induced Errors in Variational Quantum Eigensolvers. The authors of this project are Serhii Kuzmin, which is me, Tristan Mineo, and our advisor, Dr. Juan Serna, from the physics department of the University of Scranton. All right, so a quick introduction into this project. Quantum computing holds the potential to solve problems that are beyond the reach of classical systems. The variational quantum eigensolvers, VQE for short, is a hybrid algorithm that combines quantum circuits with classical optimization techniques to estimate ground state energies. However, real quantum devices are susceptible to noise. In this project, we delve into the impact of readout errors on VQE performance by varying measurement error rates and analyzing their effects on the state probabilities. The motivation of this project. We want to investigate how readout noise affects numerical stability of the variational quantum eigensolver. We want to compare the error rate of obtaining correct quantum state. And finally, we would like to suggest ways to improve the overall numerical stability and error mitigation. To start off, I'd like to explain what VQE principle is. On the diagram right here, we can see a depiction of how a VQE system works. So our first component is obviously the quantum computer, and it has a gate that has a certain number of qubits. The first component is a collection of various unit gates. Then we have a quantum ansatz. And then finally, we take the measurements of the quantum state. Then we compute the expected state of the Hamiltonian. And the final step of this system is all of this is getting sent into the classical optimizer, which runs an optimizing algorithm like a gradient descent, for example, to compute the results. And we will have our theta. So for the purposes of this experiment, we will have two systems. We will have a 1 qubit ansatz, which is just a rotational gate in the x direction. Then for our 2 qubit ansatz, we will have a 2 qubit circuit that will have a combination of rotational gates in the y and z directions. So we ran 2 experiments. Each experiment was 20 repetitions of 1,000 shots. Our 1 qubit system had a Hamiltonian of a Z Pauli matrix. So we can see 4 different plots right here. For the purposes of this demonstration, we're only going to focus on the red bars right here, as well as the blue and the green bars over here. So the blue and green bars represent the ideal quantum computer without the noise. The red bar represents what happens to a quantum state, that is the probability of that quantum state when we have a noise of certain level. So in the first plot, we have a noise of 5.3%. We can see, according to our blue and green bars, in the ideal quantum computer, we'll have a 1 state, but with a noise of 5.3%, we will have a probability of a bit flip of 5.3%. And that decreases the correct state probability. So if we try to increase our noise level, the probability of the bit flip increases, and therefore the probability of the correct quantum state decreases. And this trend can be seen when we increase our noise to 10.4%, if we increase it to 15.2%, and if we increase it to 20.2%. We can see there's a growing probability of a bit flip and the decreasing probability of a correct quantum state. Now, for our second experiment, we had a 2-qubit system with a Hamiltonian of z tensor z. So in this system, we can have 4 total possible probabilities. And we started off with a readout error of 5%. As we can see, this is the distribution of the probabilities. In the ideal quantum computer, if there's no noise, these are the quantum states that we can get. These are 0, 1, and 1, 0 quantum states. But as we can see with the noise, we can see this distribution becomes more diverse in a sense, because we have the probability of a 0, 0 quantum state and a 1, 1 quantum state. At the same level, if we increase the readout error to 10%, we can see the probabilities of all the other states besides 1, 0 increase, but the probability of that state decreases. And then this trend can be observed as we are increasing our readout error from 10 to 15%, and then from 15% to 20%. So we can see the distribution becomes more and more sparse in a sense, because we can see the growth of other probabilities and the decrease in the probability of the quantum state 1, 0. So the results. We found that as the readout error increases, the probability of a bit flip in a 1-qubit quantum circuit increases. In a 2-qubit quantum circuit, we determined that as the readout error increases, the overall probability of measuring the correct state decreases. So for our conclusions, the VQE systems are susceptible to noise, making the quantum systems more error-prone. When implementing a real-world VQE system, the noise should be considered as the potential disruptor. And finally, when implementing the algorithm, the software that aids in error mitigation should be utilized. And finally, our acknowledgement. This work was supported in part by a NASA mini grant awarded through the Pennsylvania Space Grant. The authors of this project would like to acknowledge and thank for the support that they provided. Thank you so much.